So far, we have covered kinematics, which describes motion, forces, which explain motion, and work and energy and momentum, which provide additional rules for how objects move. In this video, we will begin the last major topic of this course, rotation. The topic of rotation doesn't really add anything new to anything we have covered so far. It just takes every single topic we've seen and applies them in new ways. That means rotation is mostly just a review of everything we've seen so far. Because the connections between rotation and the previous topics are so deep, I'm intentionally going to structure this topic so it parallels the sequence of topics in earlier videos, so we can highlight the connections as they occur. The very first thing we did in this course was to review systems of measurement. Let's develop a system of measurement for rotation. In rotation, we study the motion of spinning objects. How far something spins can be expressed as an angle. So far in this course, we have measured angles in degrees. But in rotation, it makes more sense to measure angles in a different unit called radians. A radian is a unit of angle measurement like degrees. 1 radian is roughly equal to 57.3 degrees. Just like we can convert feet into meters, it is easy to convert degrees into radians. We use this conversion. The measurement of an angle in radians equals the number of degrees times pi, that's 3.14, divided by 180. Let's try it out with this question. Convert the angle 45 degrees into radians. In this question, we have been asked to convert an angle of 45 degrees into radians. Here's how we do it. We take the angle, 45 degrees, and we multiply it by the conversion factor, which is pi over 180. So when I multiply this across just like a fraction, I would get 45 pi over 180. Now, 45 happens to be a factor of 180. I can divide top and bottom by 45, and that'll give me 4 on the bottom. So that means this whole thing reduces down to pi over 4 radians. And how much is pi over 4? It is 0.785 radians. So what we have now shown is that 45 degrees is the same thing as 0.785 radians. Now, all that said, we usually don't express radians in terms of decimals like this. We usually express it in terms of a fraction relative to pi. So if somebody asks you, rather than saying 0.785 radians, we're more likely to say pi over 4 radians. So we could just stop here. Every degree measurement in the unit circle has a corresponding radian measurement. We can use the formula to convert any degree measurement into radians. It's usually convenient to express radian measurements in terms of pi. A full circle is 360 degrees. When we convert that into radians, we get 6.28 radians, or equivalently 2 pi radians. 180 degrees is 3.14 radians, that's pi radians. 90 degrees is 1.57 radians, or pi over 2 radians. 60 degrees is 1.05 radians, which is pi over 3. 45 degrees is 0.785 radians, which is pi over 4. 30 degrees is 0.524 radians, which is pi over 6, and so forth. After we finished our math review in this course, we set about establishing a coordinate system for linear motion. We will now do the same things for rotational motion. Here we see a turntable with some markers stuck to it. How would we describe the angle of orientation of the markers with respect to the center of the turntable? In pure rotation situations, we start by drawing our usual set of axes. The origin is generally located at the center of rotation, in this case, the center of the turntable. Just like we did in vectors, we consider the rightward x direction to be our starting point. There are two possible directions we can travel in, counterclockwise and clockwise. If we point our axes in the conventional way, where positive x points rightward and positive y points upward, then counterclockwise is considered the positive direction. Clockwise is considered the negative direction. In rotation, we don't usually use the term angle of orientation. Instead, we use the term angular position. Angular position tells you how far something is from the positive x-axis and in which direction, clockwise or counterclockwise. That means angular position is a vector. It is symbolized with the Greek letter theta with a vector sign. It is measured in radians. Again, as a matter of convention, we always write the direction of angular position as lying along the axis of the rotating object. That is, it lies on the z-axis, so we always write a k hat after any angular quantity. Let's apply this to some examples. In this photo, the angular position of the stickers is positive 60 degrees, or if you convert it, positive pi over 3 k hat radians. In this photo, the angular position is positive 120 degrees, which works out to 2/3 of pi. We usually say positive 2 pi over 3 k hat radians. And here, the angular position is 45 degrees clockwise from positive x, which would be negative 45 degrees, or in radians, negative pi over 4 k hat radians. In linear kinematics, we introduced displacement, a vector that describes change in position. The same concept applies to rotational motion. Take a photo of the turntable at some time, then take another photo after a period of time has elapsed. The angular displacement of the object is its final angular position minus its initial angular position. Angular displacement is a vector. It measures the angle swept out by a rotating object. Angular displacement looks and acts a lot like linear displacement. A positive angular displacement means the object has rotated in the positive direction, that is, counterclockwise. A negative angular displacement means the object has rotated in the negative direction, clockwise. Consider this question. A turntable rotates from an angular position of negative pi over 4 radians to pi radians. What is its angular displacement? In this question, we have a turntable and we're going to take two different photos of it. Okay. I'm going to set the axes on each one. I'm going to call this photo 1, and I'm going to call this one photo 2. In photo 1, the marker was located at an angle of 45 degrees below the x-axis, so that's actually negative 45 degrees, so that would be negative pi over 4 radians. And by photo 2, it has rotated counterclockwise to reach this point over here. This is the orientation of pi radians. and we are being asked to find what is the angular displacement that occurred over here. So, angular displacement, which is symbolized by delta theta, it is a vector, is equal to final angular position minus initial angular position. That is equal to final position, pi radians, minus initial position, which was negative pi over 4 radians. So that will work out to pi minus pi over 4 is equal to pi plus pi over 4. And if you want to write that as a fraction, that would be 1 1/4 pi, which is written as 5 pi over 4. If you want me to write it explicitly, when you add up two numbers, they have to have the same denominator. So to get a common denominator of 4 in both these cases, I create a fraction here where top and bottom have 4. So 4 pi plus pi gives us 5 pi, 4 and 4 stay as a 4 in the bottom. So this then is how far our sticker, our marker, has rotated. It has rotated by 5 pi over 4 radians. Of course, a turntable doesn't need to spin counterclockwise. Consider this situation. A turntable rotates from an angular position of 5 pi over 6 radians to pi over 3 radians. What is its angular displacement? To begin, I'm going to draw the turntable in these two different photos. Here are our axes. And finally, I will draw where the marker is in these two positions. In position 1, it was located at 5 pi over 6 radians. That's this angle over here. 5 pi over 6 radians is equal to 150 degrees. So relative to the positive x-axis, that places it somewhere here, close to 180, not quite. In the second photo, the marker is located at pi over 3 radians, which is 60 degrees. Now, we were additionally told that this disk was rotating clockwise. That's the negative direction. Let's take a look at what the displacement would be, the angular displacement of this marker. The angular displacement, delta theta, is equal to the final angular position minus the initial angular position. That's equal to final position, pi over 3 radians, minus initial position, 5 pi over 6 radians. Again, we can do a common denominator by multiplying top and bottom by 2 over here. That gives us 2 pi over 6 minus 5 pi over 6, which is equal to 2 minus 5 gives us 3 pi over 6. All of which is equal to pi over 2 radians. And notice, of course, that everything is negative here. 2 pi minus 5 pi gives us negative 3 pi over 6, and that's equal to negative pi over 2 radians. And that makes sense because this object was rotating clockwise. Back in linear kinematics, we introduced velocity as how fast something moves, the rate of change of position. In rotational kinematics, we can talk about rate of change of angular position, the rate at which something spins. This is called angular velocity. Now, when we looked at regular linear velocity, we saw there were two types. One is average velocity, which is displacement divided by time. The other is instantaneous velocity, which my 103 students should know. It is the derivative of position over time. Angular velocity works exactly the same way. The symbol for angular velocity is this. That's not a W, that is the lowercase Greek letter omega. It is a vector. One type of angular velocity is average angular velocity. It is equal to angular displacement over time. The other type is instantaneous angular velocity. That is equal to the derivative of angular position over time. Angular velocity is a vector. A positive angular velocity means the object has rotated in the positive direction, counterclockwise. A negative angular velocity means the object has rotated in the negative direction, clockwise. Let's apply average angular velocity to this example. A turntable rotates from an angular position of negative pi over 4 radians to pi radians. It takes 1.3 seconds to do so. What is its angular velocity? This second part is really dovetailing off of where our initial question left off. We were told in this situation that the marker had rotated through an angular displacement of 5 pi over 4 radians. Now, what was the time involved in that? We were told that the time was 1.3 seconds. So, the angular velocity is equal to displacement, angular displacement, divided by time, which equals 5 pi over 4 radians divided by 1.3 seconds. That's easy enough to find. 5 pi over 4 is 3.93, roughly. Divided by 1.3 seconds is 3.02. So that is the angular velocity of this rotating disk. It is 3.02 radians per second. Now when you actually work that out, that works out to slightly less than half of a turn every second. And we also see that this value is positive, which means this object is rotating counterclockwise. Sometimes you will be told the angular velocity in revolutions per minute. In these cases, you need to convert to radians per second before you can solve the question. Fortunately, the conversion is quite easy. If you're given the angular velocity in revolutions per minute, RPMs, you just need to multiply by 2 pi over 60 to get the number of radians per second. That conversion factor should make sense. There are 2 pi or 6.28 radians in a full revolution of 360 degrees, and there are 60 seconds in a minute. Consider this question. A CD spins at 500 RPM. What is its angular velocity in radians per second? In this question, we have been told to convert 500 revolutions per minute into the more standard unit of rotation, which is radians per second. The conversion is we multiply it by 2 pi over 60. So, similar sort of process as what we did over here. We multiply everything across like a fraction, and that's going to give us 500 times 2 is 1,000. Pi divided by 60.
Now, 1,000 divided by 60 gives us 16.67. So we could say that the rotation of this object is 16.67 pi radians per second. Or, if you prefer, we could multiply this out. So take that answer and multiply it by pi to get 52.36. So this tells us the number of radians per second, or you can express this in terms of pi. Either way will do just fine.
Finally, in linear kinematics, we introduced acceleration. Acceleration is final velocity minus initial velocity over time. It is a change of velocity over time, the rate of speed up or slow down. In calculus terms, we write it like this: the derivative of velocity over time. In rotational kinematics, we have angular acceleration. It measures how quickly the spin rate is speeding up or slowing down. Angular acceleration is symbolized with the Greek letter alpha. It equals the final angular velocity minus initial angular velocity divided by time. Or, for my 103 students, it is the derivative of angular velocity with respect to time, and it is a vector. Remember also that the direction of linear acceleration doesn't have to match that of the actual motion. Positive acceleration means speeding up in the positive direction or slowing down in the negative direction. The same is true of angular acceleration. A positive angular acceleration means speeding up in the positive counterclockwise direction or slowing down in the negative clockwise direction. Consider this question. It takes 0.5 seconds for a CD to speed up from rest to an angular velocity of 50 radians per second counterclockwise. What is its angular acceleration?
In this question, we start with a CD, which we're going to take 2 photos of. I'm going to draw my axes. There's X, there's Y, there's X, and there's Y. We were given an initial and final velocity, but just for the sake of clarity, I'm going to draw the marker initially starting at an angle of 0 degrees, and maybe in photo 2 it's, I don't know, somewhere around here. The disk is rotating counterclockwise, that is the positive direction. We were told that it's initially at rest, that is omega initial is equal to 0 radians per second, and in photo 2 omega final is equal to 50 radians per second. So let's work out the acceleration. Acceleration is equal to final velocity minus initial velocity, all divided by time. So we're assuming here that the acceleration is uniform. In that case, this is a perfectly good equation for solving for that acceleration. That works out to 50 radians per second minus 0 radians per second. So over here it was moving at 50, over here it's moving at 0, all divided by the time that elapsed between the two photos, and we were told that the time between the two photos is 0.5 seconds. So, this is now going to become 50 minus 0 is 50 radians per second divided by 0.5 seconds is equal to 50 divided by 0.5. That's going to give us 100 radians per second squared. So this is the angular acceleration of the disk. This is how much its speed is going to increase by, or rather its angular velocity is going to increase by every second. Every second its angular velocity will increase by another 100 radians per second, which is something that makes total sense because half a second elapsed and we reached 50. Had we gone for another half a second, we would have reached 100. So in 1 second, we would have reached 100, which is precisely what this acceleration is telling us.
We should point out an important subtlety in rotation. Look at this situation closely. All three stickers experience the same angular displacement, positive 5 pi over 4 k hat radians, as we saw before. But if you draw out the path that each marker took, you notice something odd. The path of the outermost marker is much longer than the path of the innermost marker. Even though all the markers had the same angular displacement, they physically moved through different distances. That's because the markers are located at different radii from the center. The greater the radius of the marker, the greater the distance it travels. The relationship between angular displacement and distance traveled is given by this equation. Distance equals angular displacement times radius. Importantly, this equation only works if delta theta is in radians. That's why we have to use radians for this entire unit of rotation. There's a very similar relationship between speed and angular velocity. Speed equals angular velocity times radius. And a similar one for acceleration. The size of the linear acceleration equals angular acceleration times radius. Again, all rotational quantities have to be in radians for these equations to work. Let's see an example. You place two stickers on a CD. One sticker is 0.02 meters from the center. The other is 0.05 meters from the center. You turn on the CD player. The CD rotates at 50 radians per second. A. What is the linear velocity of each sticker? And B. What are their linear displacements if they rotate through a revolution that is 2 pi radians?
Let's draw the turntable at two different positions. So here is photo 1 and here is photo 2. I'm going to set my axes as before. And now I'm going to draw the stickers. Since we were never really told what the starting position is, I'm just going to choose an arbitrary one of 0 radians. We were, however, told that the stickers will revolve by 2 pi radians, and we were told that the angular velocity was a steady 50 radians per second. The distance from the center to the inner sticker is 0.02, and the distance from the center to the outer sticker is 0.05. So now that we have all of this information, we were being asked to find out what was the linear displacement and the linear velocity of each sticker. So because we have two different stickers that we're dealing with, I'm going to create a table. I'm going to deal with the 0.02 meter sticker, that is the inner sticker in the first column. I'm going to deal with the outer sticker, that is the 0.05 meter sticker in the second column. Now, we can find the linear displacement. The linear displacement is solved using this equation, delta x, that is how far in terms of meters the inner sticker has traveled, is equal to the angular displacement times the radius. Now, strictly speaking, this term is not called times. This operation is not called times. It's called the cross product. And my 103 students should be familiar with this from a video that I did a couple of weeks ago. In this situation, however, the cross product works out to be the same thing as just a straight multiplication. So let's go ahead and do that. The delta theta is 2 pi radians, and the radius is 0.02 meters. So now, it is a simple case of 2 pi times 0.02, which is 0.126. So that means that as the inner marker traveled through a circle, it traveled 0.126 meters. So it traveled through 2 pi radians, which for this inner circle is 0.126 meters. That is the total distance that it traveled through. We can do something similar for the outer sticker using exactly the same equation. That is that the distance is equal to the angular displacement cross the radius, which is equal to 2 pi, since this outer marker also traveled through 2 pi radians, it traveled through a full revolution, multiplied by the radius, which is over here, 0.05 meters. So, when you multiply all of this out, you're going to get 0.314 meters, which is somewhat more than twice the displacement, or rather twice the distance of the 0.02 meter, the inner sticker. So the inner sticker, as it traveled around in this circle, it traveled a total distance of 0.126 meters. But as the outer sticker traveled through the same circle, it traveled a distance of 0.314 meters, roughly twice as far. And that makes sense because the outer sticker was located at roughly twice the distance, somewhat more than twice the distance. So you expect it to travel somewhat more than twice the distance when it travels in a full circle. Now, what about the linear velocity? We use a similar equation. The linear velocity is equal to angular velocity cross radius, which works out to the angular velocity is 50, the radius was 0.02 meters, so 50 times 0.02 is going to give us 1 meter per second. So as this disk is rotating, the CD is rotating at 50 radians per second, this inner spot is going to be moving at a linear speed of 1 meter per second. What about the outer spot? The outer spot can be, the linear speed of it can be solved in the same way. That's going to work out to 50 radians per second multiplied by its radius, which is 0.05. And that's going to work out to 2.5 meters per second. So although these two spots have the same angular velocity, they're going to have very different linear velocities because one of them is further out from the other. The one that's further out has to travel through a much greater distance than the inner one in exactly the same time.
In this video, we introduced the variables of rotational kinematics: angular displacement, angular velocity, and angular acceleration. And we saw how to convert from the linear quantities to rotational ones. In the next video, we will develop these further into the rotational versions of Newton's toolbox equations.